In this video, we're going to focus on FSM design, still classical design, using full encoding this time with the flip-flops. So the steps in the processor are the same as we've been discussing in the previous section. And as we've done before, for these videos, we're going to complete step 1 through 5. Once these are completed, then once you have the schematic, if you have a tool to do the simulation testing and then implementing it should be straightforward from there. Okay, so let's pick an example. We have had this example. We're going to keep reusing this example for various ways to design using various flip-flops and various encoding scheme. In this case, we're going to do full encoding, and we're going to design a racetrack light control where you press the start button, and as soon as you press the start button, it's going to start going to red light will turn on, stay on for 5 seconds, then it's going to go to orange, then it's going to go to yellow after 5 seconds, and finally to green. You can interrupt this process at any point by pressing the start button again, and that will start the whole sequence from red on. If you don't press the start button, once it gets to green, it stays there. Okay, so that's the problem you need to solve, and as we've discussed it before, we're going to follow the steps that are here. So our very first step is to organize the design specification using one or more of the following tools. So we always use the system just to become system diagram, and just to be complete, I'm going to do a system diagram here. We have one input. Start is the input, and as it says logic 1, you have to, once you press it, you get a logic 1. When you're not pressing it, you get logic 0. And then you're going to have 4 outputs, and the outputs will be red, orange, yellow, and green. Now as far as the and then of course sometimes we don't put it in there. Just to be complete, I'm going to put this one in here, but typically we don't put that as an input. We're going to have a clock, and its convenience is we're going to have these things change every 5 seconds. It's convenient to have our clocks basically be a 5-second clock. In other words, the single cycle is 5 seconds. Okay, and so that's our clock. Okay, usually put the names outside. Okay, so now that it's done, then for first step, I have to organize this problem into a state diagram. If you've seen the earlier video, we've done that, so I'm not going to spend a lot of time on it. Basically, regardless of which state you are in, start indicating any state you are in. As soon as S is equal to 1, you're going to go to state where, let's call this red state, where the red light is on. And then when next clock comes along, and as long as S is equal to 0, we go to the orange state. And if S is equal to 0 still, when the next clock comes along, we're going to go to yellow stage. And if S is still 0, then we go to a green state. And that's pretty much it. And then we have an output for every state. This is a more machine because they rely on which state you are in. In this case, you want the red light, the red to come on. Everything else is going to be not. I'm not going to put the rest of them in there. In this case, we want the orange light to come on. In this case, we want the yellow light to come on. In this case, we want the green light to come on. Again, if I don't put the name of the lights in here, we're going to assume they're equal to 0. We'll come back and redraw that fully fleshed out. So we have, this is complete as far as the state diagram is concerned. Everybody looking at this knows when you're in a given state and you get a given input where you're going to end up, and that's all that is. That's all that the state diagram has to do. Then we go to step 2. The step 2, we determine, okay, what kind of coding we want to use. In this problem, we have been told to use full encoding. Then once we know we are full encoding, then we have to figure out how many states we need, and And then we have, so let's go back here. So how many states do I have? 1, 2, 3, 4 states. Therefore, I need 2 flip-flop. Then accordingly, I need 2 state variables, y1, y0, to do it. So we're going to have a state 0, 0. We're going to have a state 0, 1, 1, 0, and 1, 1. So that pretty much takes care of everything we need to do in step 2. We are to step 3, and all we have to do for step 3 is we have to assign these states, red, orange, and green, yellow and green, the names we gave them. We have to assign which is 0, 0 red, orange, or whatever. And as far as we're concerned, it's more or less random, but we can go ahead and assign it. You have to assign it so you have consistently through the problem. So we're going to say this is red, this is orange, this is yellow, and this is green. Okay, so I believe we've done step 3. So step 1, 2, and 3 is kind of all related to each other in many ways. So that's our unique code. What I want to do, go back here, and I want to now redraw this thing with the way we are used to seeing state diagram, which is we're going to have a legend. It's going to be y1, y0. This is a Moore machine because the colors depend on which state we are in. And the way I'm going to put this in is I'm going to say, okay, red is here, green is here. I'm sorry, red, orange. Let's put it in the same order, yellow and green. And this is yellow. Okay, and then S, which is the input, will sit up here. Okay, red, orange, yellow is the output. Okay, so that's our legend. Remember, you have to do a legend every time you do that. Let's redraw this one. So every state, really doesn't matter which state we are in. So this star means all states. We'll end up in state 0, which we have assigned 0, 0 to, and output is going to be red, which means on 0, 0, 0. And that was 1. If you get a 0 here, what's going to happen, we're going to go to state 0, 1, and in 0, 1, the color is going to be 0, 1, 0, 0. And then if you still get an input 0, remember, if you get a 1, you always go back to 0, 0. So 0, 1, we'll end up in state 1, 0, which is the yellow state. And in this case, output is going to be that. And then finally, we come to the last state, which is green. So 101, the output is going to be 0, 0, 0, 1. And then if you get a 0 input, you're just going to sit here. And again, for every state, when you get a 1, you're going to go to 0, 0. All right, so we are done with step 1, 2, and 3, and we cleaned it up, put it all in a nice form. They ask us to use a D flip-flop for this, so this is the equation we are interested in using. And it says select flip-flop type to be used. We decided D because that's what they told us to use. Draw the present state, next state. And the goal is to determine the excitation input. In this case, it's kind of nice because once I do the present next state, y plus is the same as D. And then the outputs, and all of our outputs in this case is more, and so we'll do that as well. Okay, so now I have the state diagram. So we are in the step, I forgot which step this was. This is step 4, and in step 4 we are basically flushing out the whole present state, next state business. So step 4, we are doing a present state, next state. So we've got 2 states, y1, y0. We've got one external input, S. We've got next state, y1 plus and y0 plus. And then, of course, we've got the whole output business, which is red, orange, green, yellow. We got to make sure we put them in the right order, otherwise it's going to be really confusing. Red, orange, yellow, and green. Okay, so just to be safe, this is external input once again, external output once again. Because it's a D, D0 is the same as Y1, and I'm sorry, D1 is the same as Y1 plus, and D0 is. So this is both excitation input and next state, so it's together, and this is external input and the present state. Okay, just like we do the truth tables, we're just going to fill this in. All right, so now that we've got that all completely filled in, we got to figure out what the y1 and y0 are. That's kind of relatively simple, because if you're 0 and your input is 0, you'll end up in 0, 1. If the input is 1, you go back to red state, which is 0, 0. If you're in 1, 0, and if you're in 0, 1 and you get a 0, you go to 1, 0. Otherwise back to 0, 0. If you're in here and you got a 0, you go to state 1, 1. Otherwise you go back to 0, 0. If you're in 1, 1, you stay in 1, 1. Otherwise you go to 0, 0. Great. So we've got this thing figured out, so as far as it goes. And of course, if you're in red state, these are basically tied to the red state. So as long as you're in the red state, you get a 1 in here. Other times you get a 0. It's kind of becoming pretty obvious how you do this. And then when you're in this orange, would be this orange state gives us the 1. Rest of the time we are 0. Yellow, when we are in the yellow state, which is 1, 0, we get a 1. Everywhere else is 0. And finally you get a green when you're in green state, or coded 1, 1, 1. Okay, so that's it. All right. So that's step 4. Finally, we are getting to a place where we can kind of draw our schematic. We're not quite done, because we have to write the equation for D1, D0, R, O, Y, and Z, and G. So what you do, unless you can see the minimized version of this, you really have to do a Kmap. So you have to do a Kmap for Y1, Y0, S, this is for D1, and this case is going to be 0, 0, 1, 0, 1, 0, and 1, 1, 0 here. Okay, so if you do this, you got this and you got this here, so we can write the D1 for that. Then again, you have to write another one for D0, and if you need to do it for external output, you should do that as well, but the external output is so simple you may not need to do a kernel map for it. Okay, so this is 1, 0, then you got 2 zeros. Now we are down here. 4 is 1, 1, 0, and 1, 0 again. We got this and we got this. All right, so D1 is going to be Y0 S naught, or this one, which is Y1 S naught. Okay, and then D0, which is this one, is going to be basically Y1 S naught, or the one on the bottom and on the top, which is Y0 naught S naught. Okay, so we got these two. These guys are kind of easy. I don't know if it's worth drawing them, but as you can see, that are the output. So these are the excitation, and then the output's going to be R is simply going to be equal to Y1 Y0 naught, R, I'm sorry, O would be Y0 Y1 Y0, oops. y0, y1 not y0, and then yellow would be y1 y0 not yellow, not to be confused with y0 y1. That was unfortunate naming. And then green would be basically y1 y0. Okay, so this is it. We know we have two flip-flops and we're going to need a lot of room in the middle, so that's fine. What we're going to do, we got D0 y0, and then we've got D1 y1. So these are our two flip-flops. D1, so we basically got S running along the top. Let's just run it. So we've got S, but really we're not using S at all. We're only using S naught, so let's invert it quickly and get our S naught out there. Okay, and then so this one, y1 comes back, y0 comes back, and then we're going to have S naught, y naught, and it, oops, I suppose that would work as well. And then we invert this thing and then bring that down. I'm doing D0. I was starting with D1, but then I realized I'm going for D0, so we'll do that. So we've got S naught, y1, and then we've got y0 naught S. We'll take these out, OR them together, and then ship them back to D0. So we got this piece done. For D1, we do need y1 S naught. We did that right here, so we can pull that out. And then the only other thing we need is this coming down and ending. So that S naught y0 naught. So we just need an, oops. Oh, I'm sorry, it's y0. So we took the y0, we got the S naught, we're ending them together. And then basically these, oops, they have to be OR together before we are done. So we're going to take this a little further out and OR them. And that gives us D1. Okay? And then once that is done, then we have to go off and create all this other one. So we've got basically, we've got y0 here, and then we're gonna have, actually, you know what? I might do that on the bottom. Let's get the outputs on the bottom. We have a lot more room. So I have y0. You can use y0 naught or just simply create another one here. There is my y0 naught. This is my y0. And then I've got y1, and I'm going to create my y1 naught here as well. Oops. Might as well go a little higher so don't use up that much space. So all right. So if you see, this and this will give me and together. That gives me the red. So I just have a bunch of ands here. Yeah, all that. So I just have to hook them up correctly. All right. So y1, y0 uninverted, and then y1 inverted gives me the orange, and then the opposite, y1 and then y0 inverted gives me yellow, and both of them 1 gives me the green. And there we have it. This is the circuit that would do that startup for us. All right, so you notice if you remember or if you watch the video about one-hot encoding, you see that this one has less flip-flop but has a lot more gates, and the other one had double the flip-flop but not as many gates. And depending on what you're designing, which of these are a better solution for you, that's the one you need to go with.